Mathematics has become a vastly diverse subject over history, and there is a corresponding need to categorize the different areas of mathematics. A number of different classification schemes have arisen, and though they share some similarities, there are differences due in part to the different purposes they serve. In addition, as mathematics continues to be developed, these classification schemes must change as well to account for newly created areas or newly discovered links between different areas. Classification is made more difficult by some subjects, often the most active, which straddle the boundary between different areas. A traditional division of mathematics is into pure mathematics, mathematics studied for its intrinsic interest, and applied mathematics, mathematics which can be directly applied to real-world problems. This division is not always clear, and many subjects have been developed as pure mathematics to find unexpected applications later on. Broad divisions, such as discrete mathematics and computational mathematics, have emerged more recently. Classification systems. The mathematics subject classification is produced by the staff of the review databases Mathematical Reviews and Central Blatt Math. Many mathematics journals ask authors to label their papers with MSc subject codes. The MSc divides mathematics into over 60 areas, with further subdivisions within each area. In the Library of Congress classification, mathematics is assigned the subclass QA within the class Q. The LCC defines broad divisions, and individual subjects are assigned specific numerical values. The Dewey Decimal Classification assigns mathematics to division 510, with subdivisions for algebra and number theory, arithmetic, topology, analysis, geometry, numerical analysis, and probabilities and applied mathematics. The categories within mathematics list is used by the Arxiv for categorizing preprints. It differs from MSc, for example it includes things like quantum algebra. The IMU uses its program structure for organizing the lectures at its 4-yearly ICM. One of its top-level sections that MSc doesn't have is Lie theory. The ACM computing classification system includes a couple of mathematical categories: F. Theory of computation, and G. Mathematics of computing. Math Overflow has a tag system. Mathematics book publishers such as Springer, Cambridge and the AMS use their own subject lists on their websites to enable customers to browse books or filter searches by subdiscipline, including topics such as mathematical biology and mathematical finance as top-level headings. Schools and other educational bodies have syllabuses. Research institutes and university mathematics departments often have sub-departments or study groups. E.g., SIAM has activity groups for its members. Wikipedia uses a category mathematics system on its articles, and also has a list of mathematics lists. Major divisions of mathematics. Foundations: recreational mathematics, from magic squares to the Mandelbrot set. Numbers have been a source of amusement and delight for millions of people throughout the ages. Many important branches of serious mathematics have their roots in what was once a mere puzzle or game. History and biography. The history of mathematics is inextricably intertwined with the subject itself. This is perfectly natural. Mathematics has an internal organic structure, deriving new theorems from those that have come before. As each new generation of mathematicians builds upon the achievements of our ancestors, the subject itself expands and grows new layers. Like an onion. Mathematical logic and foundations, including set theory. Mathematicians have always worked with logic and symbols. But for centuries the underlying laws of logic were taken for granted, and never expressed symbolically. Mathematical logic, also known as symbolic logic, was developed when people finally realized that the tools of mathematics can be used to study the structure of logic itself. Areas of research in this field have expanded rapidly, and are usually subdivided into several distinct departments. Model theory. Model theory studies mathematical structures in a general framework. Its main tool is first-order logic. Set theory. A set can be thought of as a collection of distinct things united by some common feature. Set theory is subdivided into three main areas. Naive set theory is the original set theory developed by mathematicians at the end of the 19th century. Axiomatic set theory is a rigorous axiomatic theory developed in response to the discovery of serious flaws in naive set theory. It treats sets as whatever satisfies the axioms, and the notion of collections of things serves only as motivation for the axioms. Internal set theory is an axiomatic extension of set theory that supports a logically consistent identification of a limited and infinitesimal elements within the real numbers. See also List of set theory topics. Proof theory in constructive mathematics. Proof theory grew out of David Hilbert's ambitious program to formalize all the proofs in mathematics. The most famous result in the field is encapsulated in Gödel's incompleteness theorems. A closely related and now quite popular concept is the idea of Turing machines. Constructivism is the outgrowth of Brouwer's unorthodox view of the nature of logic itself. Constructively speaking, mathematicians cannot assert either a circle is round, or it is not, until they have actually exhibited a circle and measured its roundness. Arithmetic. Arithmetic is the study of quantity. Algebra, the study of structure, begins with numbers, first the familiar natural numbers and integers and their arithmetical operations, which are recorded in elementary algebra. The deeper properties of these numbers are studied in number theory. The investigation of methods to solve equations leads to the field of abstract algebra, which, among other things, studies rings and fields, structures that generalize the properties possessed by everyday numbers. Long-standing questions about compass and straight-edge construction were finally settled by Galois theory. The physically important concept of vectors, generalized to vector spaces, is studied in linear algebra. Order theory. For any two distinct real numbers, one must be greater than the other. Order theory extends this idea to sets in general. It includes notions like lattices and ordered algebraic structures. See also the order theory glossary and the list of order topics. General algebraic systems. Given a set, different ways of combining or relating members of that set can be defined. If these obey certain rules, then a particular algebraic structure is formed. Universal algebra is the more formal study of these structures and systems. Number theory. Number theory is traditionally concerned with the properties of integers. More recently, it has come to be concerned with wider classes of problems that have arisen naturally from the study of integers. It can be divided into elementary number theory, analytic number theory, algebraic number theory, geometric number theory, combinatorial number theory, transcendental number theory, and computational number theory. See also the list of number theory topics. Field theory and polynomials. Field theory studies the properties of fields. A field is a mathematical entity for which addition, subtraction, multiplication and division are well defined. A polynomial is an expression in which constants and variables are combined using only addition, subtraction, and multiplication. Commutative rings and algebras. In ring theory, a branch of abstract algebra, a commutative ring is a ring in which the multiplication operation obeys the commutative law. This means that if A and B are any elements of the ring, then A times B equals B times A. Commutative algebra is the field of study of commutative rings and their ideals, modules and algebras. It is foundational both for algebraic geometry and for algebraic number theory. The most prominent examples of commutative rings are rings of polynomials. Analysis. Within the world of mathematics, analysis is the branch that focuses on change, rates of change, accumulated change, and multiple things changing relative to one another. Modern analysis is a vast and rapidly expanding branch of mathematics that touches almost every other subdivision of the discipline, finding direct and indirect applications in topics as diverse as number theory, cryptography, and abstract algebra. It is also the language of science itself and is used across chemistry, biology, and physics, from astrophysics to X-ray crystallography. Combinatorics is the study of finite or discrete collections of objects that satisfy specified criteria. In particular, it is concerned with counting the objects in those collections and with deciding whether certain optimal objects exist. It includes graph theory, used to describe interconnected objects. See also the list of combinatorics topics, list of graph theory topics and glossary of graph theory. A combinatorial flavor is present in many parts of problem solving. Geometry and topology. Geometry deals with spatial relationships, using fundamental qualities or axioms. Such axioms can be used in conjunction with mathematical definitions for points, straight lines, curves, surfaces, and solids to draw logical conclusions. See also list of geometry topics. Convex geometry and discrete geometry includes the study of objects such as polytopes and polyhedra. See also list of convexity topics. Discrete or combinatorial geometry, the study of geometrical objects and properties that are discrete or combinatorial, either by their nature or by their representation. It includes the study of shapes such as the Platonic solids and the notion of tessellation. Differential geometry, the study of geometry using calculus, and is very closely related to differential topology. Covers such areas as Riemannian geometry, curvature and differential geometry of curves. See also the glossary of differential geometry and topology. Algebraic geometry. Given a polynomial of two real variables, then the points on a plane where that function is zero will form a curve. An algebraic curve extends this notion to polynomials over a field in a given number of variables. Algebraic geometry may be viewed as the study of these curves. See also the list of algebraic geometry topics and list of algebraic surfaces. Topology deals with the properties of a figure that do not change when the figure is continuously deformed. The main areas are point set topology, algebraic topology, and the topology of manifolds, defined below. General topology, also called point set topology. Properties of topological spaces. See also the glossary of general topology and the list of general topology topics. Algebraic topology. Properties of algebraic objects associated with a topological space and how these algebraic objects capture properties of such spaces. Contains areas like homology theory, cohomology theory, homotopy theory, and homological algebra, some of them examples of functors. Homotopy deals with homotopy groups as well as simplicial complexes and CW complexes. See also the list of algebraic topology topics. Manifolds. A manifold can be thought of as an n-dimensional generalization of a surface in the usual three-dimensional Euclidean space. The study of manifolds includes differential topology, which looks at the properties of differentiable functions defined over a manifold. See also complex manifolds. Applied mathematics. Probability and statistics. Probability theory. The mathematical theory of random phenomena. Probability theory studies random variables and events, which are mathematical abstractions of non-deterministic events or measured quantities. See also category, probability theory, and the list of probability topics. Stochastic processes. An extension of probability theory that studies collections of random variables, such as time series or spatial processes. See also list of stochastic processes topics, and category, stochastic processes. Statistics. the science of making effective use of numerical data from experiments or from populations of individuals. Statistics includes not only the collection, analysis and interpretation of such data, but also the planning of the collection of data, in terms of the design of surveys and experiments. See also the list of statistical topics and category, statistics. Computational sciences. Numerical analysis. Many problems in mathematics cannot in general be solved exactly. Numerical analysis is the study of iterative methods and algorithms for approximately solving problems to a specified error bound. Includes numerical differentiation, numerical integration and numerical methods. Cf. Scientific computing. See also list of numerical analysis topics. Computer algebra. This area is also called symbolic computation or algebraic computation. It deals with exact computation, for example with integers of arbitrary size, polynomials or elements of finite fields. It includes also the computation with non-numeric mathematical objects like polynomial ideals or series. Physical sciences. Mechanics addresses what happens when a real physical object is subjected to forces. This divides naturally into the study of rigid solids, deformable solids, and fluids, detailed below. Mechanics of structures. Mechanics of structures is a field of study within applied mechanics that investigates the behavior of structures under mechanical loads, such as bending of a beam, buckling of a column, torsion of a shaft, deflection of a thin shell, and vibration of a bridge. Mechanics of deformable solids. Most real-world objects are not point-like nor perfectly rigid. More importantly, objects change shape when subjected to forces. This subject has a very strong overlap with continuum mechanics, which is concerned with continuous matter. It deals with such notions as stress, strain and elasticity. Fluid mechanics. Fluids in this sense includes not just liquids but flowing gases, and even solids under certain situations. It includes such notions as viscosity, turbulent flow and laminar flow. See also fluid dynamics. Particle mechanics. In mathematics, a particle is a point-like, perfectly rigid, solid object. Particle mechanics deals with the results of subjecting particles to forces. It includes celestial mechanics, the study of the motion of celestial objects, or uses mathematical modeling, statistical analysis, and mathematical optimization. Mathematical programming minimizes a real-valued function over a domain that is often specified by constraints on the variables. Mathematical programming studies these problems and develops iterative methods and algorithms for their solution.